Nuclear spaceships. Welcome to Science Sci-fi, connecting the public to science and technology through storytelling. My name is Ernest Friedman. I'm a science fiction writer and an IT professional. Today, we're going to talk about nuclear propulsion. We're going to cover a number of topics. In the future, I'm going to do a very elaborate, I'm going to invite some guests to do some more specific on this topic. But today, I'm going to do just a very high level of the topic of nuclear propulsion. Stay tuned. And of course, when we talk about nuclear propulsion in a channel called Science Sci-fi, we want to talk a little bit about science fiction. So here is a picture of the Resonante from the TV series The Expanse. It's called a very good book series. I would recommend reading it. And you're going to compare how nuclear propulsion in today's technology, what may come in the next few decades, compared to this science fiction TV series, and if it's even comparable. So, what are the agenda today? In this video, we're going to talk a very high level about what are rockets, give the very basic terminology, what are thrust, delta V, specific impulse, the exhaust velocity, rocket equation. Then we're going to talk about chemical rocket, because that's what we currently have, and what is coming in the next few years, which will nuclear thermal, nuclear electric, nuclear impulse, nuclear fusion, and then we compare it to the Epstein Drive from science fiction, the Expanse series. What are rockets? So rockets are a kind of agent that can operate in space. It's carried the propellant inside it. Here is an example of a chemical rocket that the propellant includes rocket fuels and oxygen. Together, the fuel and the oxygen are combust, they're burned, and they heat to a very high degree, and then they go back through the exhaust, and by pushing themselves back, the rocket is moving to the other side. Rocket, of course, have to carry all the propellant with it. It's not like a jet engine that can take air from the outside and push it outside, because there is no air in space. So it needs to carry all the propellant in it. There is a distinction between rocket fuel and propellant. Propellant also include the oxygen, and it's not necessarily fuel, as we're going to see when we're going to talk about nuclear propulsion. Thrust, this is how much the rocket engine is pushed back. It's not just the velocity that the gas are going back, but how much gas you push. If you push a lot of gas in one time, then there is more thrust. Why is it important? Because if you want to launch from planet Earth with high gravity, you need to lift, not only accelerate, but you also need to overcome the gravity in order to get into space. So you need the high thrust when you want to escape a planet. Delta V is what is, if you use all the propellant in the rocket, there is a beginning, the speed at the beginning, which if it's from planet Earth, it's 0. And then the speed at the end, once you exhaust all your fuel. And there is a payload, because you don't want to just send the rocket without anything. You want to bring some people to space, or some cargo or payload, a satellite. So that's the payload. The rocket equation, it's quite simple. Delta V, which means the velocity, the speed that the rocket can gain, is equal to VE, that the exhaust velocity, the speed that the gas are coming out of the exhaust of the nozzle. And then we have lambda, the natural algorithm function. This is something that exists in the calculator. M0, that's the initial mass of the entire rocket. I'll move a little bit my picture here. That's the Saturn V. That's the entire rocket, including the rocket itself, the payload, and all the propellant, which is the fuel and the oxygen. Everything together, that's M0. And M final, that's the final mass of the rocket, including the payload, but not including the propellant, because we already pushed all the propeller outside in order to push the rocket to the other direction. So we have the rocket and the payload. That's what we have left at the end. So one example, let's say VE, the exhaust velocity, the speed of the gas coming out of the exhaust, It's coming out at a speed at 4.2 kilometers per second. This is the most efficient chemical rocket that we have in existence today. That's when we use hydrogen and oxygen. There are other type of rocket fuel that are like kerosene or methane, which are slightly less efficient. So it's about 3.5 kilometers per second, something like that. But for the example, we use the hydrogen, which is the most efficient fuel, most efficient engine. M0, let's say 4,000 ton, something like the Saturn V or the SpaceX Starship. The final mass is 200 ton, let's say 100 ton is the rocket itself with the engine, and another 100 ton of payload. So from 4,000 ton, we only have 1 ton reaching orbit or escaping Earth eventually. So that's a very small amount in comparison. Let's see what we have here. Delta V, 4.2. This is the formula. ln 4,000 divided by 200. And then you do from the calculator, you can see here I did it already in advance, but you can do that yourself. It's 2.99, almost 3. Multiply it by 3.4, which is or 3.2, the exhaustion speed. And we get to a speed of 12.85 kilometers per second, which is just a little bit faster the escape velocity of planet Earth. And if you include an air drag, that is more or less what you need in order to escape Earth. So you need 4,000 tons of rocket fuel, of rocket and rocket fuel, only to have a payload, a cargo of 100 tons. That's more or less the number. So with rocket fuel, it takes about 7 months to reach Mars. And if we want to go to Alpha Centauri, it could take something like 70,000 years, maybe 100,000 years. But if you do the most efficient gravity assist with the sun and you can accelerate it by maybe a factor of 10, then a travel to Alpha Centauri with chemical rockets could take something like 7,000 years. Don't do that at home, kids. Okay, one example of chemical rocket, that's the RS-25. That's what used to be used by the space shuttle, and today the Space Launch System, SLS, is using it. So you can see here, the exhaust velocity is 4.436. That's pretty high, even more than the 4.2. This is one of the most efficient engine in existence. Yeah, so that's the stats about the engine. It can carry about 73 times its own weight, and it has quite a lot of thrust, so it could actually lift a rocket, or a few of this engine plus a couple of boosters can lift a very heavy rocket into space. So it has thrust, and it has the exhaust velocity, the high exhaust velocity, so it can give us the push that is needed as per the calculation we did earlier. Now we move into nuclear fission. Nuclear reaction, we have uranium, the 235, then we sent a neutron, and the neutron react with the uranium, it hit the nucleus, it turned into uranium-236, and then it break into 2 smaller elements, Kr and Br, and during this process that the uranium is split into 2, it also throw out a couple of neutrons and also have a lot of energy. Why is that important? Because as we spoke earlier with chemical rocket, the energy that the oxygen and the hydrogen or the other fuel together burn, it's chemical reaction. It does generate heat. We have rockets, but with nuclear, we can generate a lot more energy, a lot more heat or other type of energy. And can we use it for rockets? The answer, of course, is yes. First, most simple type of nuclear fusion propulsion is nuclear thermal. This is something that NASA is currently working on. Hopefully before the 2030, they will have a nuclear engine that can be operational in space, like the Draco or High Dragon. Also, a concept engine was built in the 1960s, 1970s called NERVA. The idea here is that because nuclear is a lot more energetic than chemical reaction, it can generate more heat. So also you don't need oxygen, you just need hydrogen in this case. You take a liquid hydrogen, push it into a chamber, heat it with a nuclear reaction to temperature much higher than what you can heat it in regular chemical reaction. And then you can have exhaust velocity. The gas, hydrogen is being pushed out at a velocity much faster than what it would have been pushed out in case of a regular hydrogen chemical reaction. The number from the 1960s could, instead of 4.2 kilometers per second, it could reach something like 8 or 9 kilometers per second. It's twice as good. And the engines that NASA are working now could maybe even get to something like 15 kilometers per second. So if, remember the rocket equation, imagine that VE, this part here, it's 3 times faster, then you can have either more payload or you can get to 3 times higher delta V. The rocket can go a lot faster. Now the problem is that the nuclear reactors need a lot of heat dispersal. You need a radiator to get rid of the heat, otherwise the whole spaceship will melt. So it cannot be too big. So it does push the gas. It's a very, very high velocity, but it doesn't push a lot of gas, just a much smaller amount. So this doesn't have enough thrust to lift a spacecraft from Earth to Earth orbit. So what you need for that, you need a chemical rocket to bring the nuclear spaceship to orbit. And then once you're in orbit, then you can have the much more efficient fuel. But it pushed the hydrogen for a much longer time at a higher speed, but it's much smaller amount of hydrogen. So it's not enough to lift from Earth, but once you're in orbit, you accelerate to Mars and it's can get to Mars a lot faster, perhaps instead of 7 months, do it in 3 months or maybe even less. Nuclear electric. Nuclear electric, one example is the Vazmir. Here you have a plasma, but instead of heating the hydrogen or the plasma to a very high temperature, and then because of the high temperature, it comes out of the exhaust, you do something else. You ionize the plasma. It doesn't necessarily have to be hydrogen. I think a lot of time we use xenon or other gases. We ionize them so they have electric, and once they're electrified, they are ions. Then you push them into a chamber, and then you accelerate them using the electromagnet, using the nuclear. So the nuclear reaction does not generate heat necessarily; it heats electricity, and the electricity is used to accelerate the ions at a very high speed. So it can be even more efficient than nuclear thermal. This kind of engines are also in development. Again, it's a very low thrust, but very, very high speed. It's coming very fast out of the exhaust. It can only operate in space. It cannot lift a spacecraft out of planet Earth. So the disadvantages of the nuclear reaction is what we spoke already. Then one more thing, when you launch it into space, there could be an accident, and then the nuclear material could spread and may cause radiation and fallout. People don't like that so much. Whenever a spacecraft is lifted with nuclear material, NASA is trying to be very, very careful about not have any accidents. Nuclear energy generates a lot of heat, so you need a large radiator to, especially in space, how to get rid of all the heat that the nuclear reactor generates. That's why we cannot have huge engine with a lot of energy, because there is no way for us to get rid of the heat. As a result, we have low thrust, so we cannot launch it from Earth. It can only work once the spacecraft is already in space. But there is a solution for that. I'm not saying it's a good solution, but there is a solution. Nuclear impulse. Nuclear impulse is basically you blow up nuclear bomb behind the spaceship, and from the explosion, the spaceship is being pushed up or forward. And it has all kinds of suspenders, so you need something like 1,000 bomb, and each time you throw, every few seconds you throw one bomb, and then it nuclear explosion that's pushed the spacecraft. So this kind of spacecraft, there was a project in the 1960s called the Orion project. Those ships can get to Mars in something like 3 weeks. They can get to Alpha Centauri in something like 100 years. They can get maybe theoretically 5% of speed of light. You probably need thousands of rockets. It does have the high thrust, so it is a nuclear explosion. It's a nuclear bomb. So nuclear bomb has the capacity to launch a spacecraft, even from the Earth surface. So it's, but you are blowing up nuclear bomb, and nobody wants to blow up nuclear bombs on planet Earth unnecessarily. Wants to deploy because it still have like 1,000 nuclear bomb inside it, so it's considered a nuclear weapon. It's against all the treaties that the United States signed with Russia or with the Soviet Union before that. Of course, one also with the launch, it needs a few bombs to blow up on Earth, so there is a fallout, radiation stuff. Not very popular idea. Because of all of the above, the project was cancelled in the early 1970s. Now we move to nuclear fusion. Okay, nuclear fusion is like we spoke earlier about nuclear fission, that you have a uranium, you bombard it with neutron, and then it breaks down to two smaller atoms and release a lot of energy in the process. Nuclear fusion is the opposite. You take two small nucleus, two small atoms, merge them together, and then they become a bigger atom, and in the process they release a lot of energy. So the most efficient nuclear fusion reactor that currently operates on Earth, and maybe this will also be used in space, I'm not sure yet, is this fellow here, D2 and tritium, deuterium and tritium. That's hydrogen with an extra neutron and hydrogen with two neutrons. So this is positive. Hydrogen with proton and neutron, and proton and two neutron. You merge them together, they merge into a helium atom, and the byproduct is a neutron, one extra neutron. So this is the most efficient. It generates 17, I'm not sure about how to read this. I'm not an expert. I am going to invite an expert to give a talk on this channel. But this is the most easiest to achieve, but easiest is with quartz. We've been able to reproduce this in laboratories, but to do it in a commercial way is not yet viable. Also, one of the problems with this kind of reaction, that you have a tritium and deuterium, is that the byproduct is a neutron, and neutron could react with the container, with the tanks and stuff, and then eventually it will become radioactive, so it needs a lot of maintenance, like I don't know, every few days it will need maintenance to get rid of the nuclear material that's done from the extra neutron. So we have other type. Instead of using a hydrogen with an extra neutrons, we use helium-3. Typical helium is 2 neutron, 2 protons. Helium-3, it still has the 2 protons. That's what makes it helium, but it only has 1 neutron. So there are 2 processes. One, we take the deuterium, that's hydrogen with an extra neutron, plus tritium, and that's create a regular helium. And the byproduct is a proton, 1 proton, which is a lot better than neutron, because neutron could react with the tank or the pipes. Proton, it's basically a hydrogen atom, so we can use it as a hydrogen, take it or dispose of it or do whatever we want, but it's not reacting with the tank. So it's a lot cleaner. It requires a lot of less maintenance. So we have the deuterium and helium-3, or we can do 2 helium-3, like the diagram here, that combine together and they release 2 proton and a regular helium, which is, proton is like a hydrogen, nucleus of a hydrogen. So we may, with nuclear fusion in space, use the helium-3 just because it requires less maintenance, even though it is maybe a little bit more difficult to produce the reaction. Nuclear fusion, plasma at 100 million degrees Kelvin or Celsius, that's almost the same. With Fahrenheit, I'm not sure, it's maybe something like double. Traditional nuclear fusion, because you need to, no tank or no vessel, no container can sustain such a high degree. So we need some other way to confine this. So traditionally, it's been done with magnetic confinement. The very huge magnet, make sure that the atoms stay in one spot and they will not come and touch the wall and hit it to 100 million degrees. The new reaction that was the news in December, not too long ago, is that a laser-based confinement, so they push the atom very, very quickly and with the lasers, and it hit it very fast, so it didn't have time to touch the container. So it's done by doing it very, very quickly. So it's done in a fraction of a billionth of a second. So this may become a commercial way of producing fusion energy commercially. Commercially, that means we get more energy than what we invest in order to confine it and all the laser to hit it. We want to get more energy back than what we put in. So we are getting better and better and better on that, but it's still not commercial, but we are close. It used to be said that a fusion reactor is always 20 years in the future or 40 years in the future, but now it's probably 4 years in the future, not 40 years anymore. Why the advancement in recent years? New superconductors material, good magnetic confinements, and computing with artificial intelligence that can design magnets and simulate the plasma a lot better than what we could do with the plasma in the past. So nuclear fusion, we take this fusion and basically we create something very, very similar to the nuclear electric that we spoke about, that we have a plasma, ionized plasma, and then we have electromagnets that accelerate the ions to a very high speed and push them back through the exhaust and a very, very, very high speed. So Pulsar, we have a company right now in the UK called the Pulsar Fusion. They are building a nuclear fusion engine. They claim it's going to be ready in a few years. I hope they're right. I don't know, but there is a possibility. And the exhaust, it's coming out, if you remember, from chemical rocket, it was something like 4.2 kilometers per second. And with nuclear thermal, it's something like 8 or maybe even 15 kilometers per second. With nuclear fusion, because it's even more energetic than nuclear fission, the exhaust velocity can reach something like 300 kilometers per second, which is about 100 times faster than chemical rocket. And it could maybe in the future be even better than that. So that means instead of 7 months in chemical rockets, we can get to Mars in 2 weeks. And the most hypothetical calculation with gravity assist and a more efficient version, it's very, very hypothetical. Alpha Centauri in 11 years, which is, I don't know, like more than 30% the speed of light. It's very, very fast, very efficient. So nuclear fusion is the future. Of course, it's not being able to launch it from the surface of Earth. It's kind of like a nuclear electric, but a little bit more efficient and more energetic. So let's compare this to the Expanse, the Epstein Drive. Epstein Drive, this is statistics that I read from some wiki, from a fan of the Expanse TV series. I compare it to the Raptor 2. We can mention the fusion that we have today. So the Raptor 2 have this is what SpaceX is now using in Starship. So the exhaust velocity is 3.65 because it's using ethanol, so it's slightly less efficient than hydrogen. That's about 0.00013% of the speed of light. Then energy is chemical. Thrust is 230 tons, so it's pretty powerful. But even though Starship needs like 33 engine in order to lift it to space, but one engine can push 200 can lift 230 tons. So if you want like 5,000 tons, of course you need many engines. That's the speed, 3 point something. What do we have on the Expanse? The Epstein Drive. Thrust 6.3 meganewton. That's about 3 times more powerful than the Raptor. That means if you could lift it from a planet, it could lift from Earth. Fusion power with a very high thrust, very high exhaust velocity. Specific impulse, so I can't even read. It's something like in the million. So that's 18,900 kilometers per second. Do you remember the fusion power that the previous company from the UK, Pulsar Fusion, is currently building? It's about 300 kilometers per second. So the Epstein Drive from the Expanse TV series is 18,000. So that's a lot faster. That's about 6.8% the speed of light. And energy source is the same. It's just much more powerful engine that can have a much higher thrust, and the exhaust velocity is, I don't know, like astronomical, something very fast. So with the Epstein Drive, you can accelerate at 1G for many hours and get to Mars, I don't know, within a few hours, and to the asteroid belt in a couple of days. It's a very efficient engine, and we are not there. We are not there yet. But the Expanse, we still have about 200 years. So by 200 years, maybe we can have fusion engines that can get to this kind of performance. So that was the presentation for today, and please make sure to check my channel in the future, like and subscribe if you like this video, and I hope to bring a guest speaker that can talk about nuclear energy a little bit more in depth with more knowledge than I do. And thank you very much, and see you soon in the next video. Bye. Bye for now.